actually cover the lab, the window of the lab first with styrofoam and then with aluminum foil, so you can't see the view. My students think I'm doing that just to keep them from being distracted, but I assure them it has to do with temperature stability in the lab. But I'm going to do a tiny bit of subliminal advertisement. So stare deep into the deep blue sky there. What do we see there? Oh, something about graduate study in physics at the University of Colorado. It's gone. Oh, it's there for a second and it's gone. But just have that idea planted in your mind. It's a nice place to work. It's a great place to do some physics. Okay. I'd like to get a little background. How many people here are, say, studying something other than physics or chemistry? Enough that I'm gonna show this slide. And I'm sorry if it seems too simple, but in physics we like to work at ordinarily one measures temperature, say in Fahrenheit. This is supposed to be 80 Fahrenheit kind of room temperature, -9. There's like a -60 Fahrenheit. This little green stripe here from -60 Fahrenheit to 110 Fahrenheit. It's about the range of temperatures you're going to find on the face of the Earth. In physics and chemistry and earth sciences, we like to measure temperatures up from the bottom. So 300, 250, these are in degrees Kelvin. There's a lowest possible temperature, 0. This is absolute 0, the temperature you can't get lower than. So at those units here on Earth, we're around 250 or 300 degrees Kelvin. As you get down to 200 degrees Kelvin above absolute 0, carbon dioxide freezes. Right below 100 degrees Kelvin or -270 Fahrenheit, air starts to freeze. As this happens, atoms, gas molecules, which are zooming around in front of us, around 280 meters per second at room temperature, maybe 800-900 miles per hour, you gradually slow down until you're going to get slower and slower as you get going colder and colder. You can't see it here, but there's a little dotted line, you barely see it, called at 3 Kelvin. 3 Kelvin is special because it's the lowest possible natural temperature. If you go out into the space between the stars, the space between the galaxies, it doesn't go all the way, it gets very cold, but it doesn't go all the way down to 0 Kelvin because of the background radiation. So 3 Kelvin is the lowest possible natural temperature. It's 100 times colder than where we live, but remember that because we're going to take a whole, we're going to zoom in down there. And it's one of these, kind of like one of these SAT questions. 3 Kelvin, that's the lowest possible temperature in nature. We actually operate down at 100 billionths of a degree above absolute 0. You can think of there's a little gap there. So basically the ratio between this, the temperature where we work and 3 Kelvin is like the ratio between the height of Mount Everest and the thickness of a pencil lead, say a millimeter. So these are extraordinarily low temperatures, even compared to the lowest possible temperatures in nature. This is a very artificial thing to do, but I'll try to explain, as hard as it is and as weird as it is to do, it's interesting things happen. I'm going to actually take another survey. I know you've all been meaning to get around to it, but a lot of things I've been meaning to do I haven't gotten to yet. How many people have yet to take that first class in quantum mechanics? You can admit it. You've been meaning to take a class in quantum. Okay, for the 3 people here who haven't taken quantum mechanics, we're going to review it. I put it all on one slide for practice. Here it is. Atoms, or anything, can be thought in 2 different ways. They can be thought in sort of the sense of classical sense of like billiard balls on a table. That's sort of the classical idea of classical physics. Or you can think of them as waves, which is a quantum mechanical idea. As things get colder, they get wavier, which is sort of the nature of things. Until when they get really, really cold, this wavy picture triumphs, and that's Bose-Einstein condensation. It is the ultimate wave. Okay. Let's see. Why is it that making an atom colder makes it more wavy? It has to do with Heisenberg's uncertainty principle. I'm going to show for the non-scientists in the audience, I beg your indulgence, I'm going to show an equation. Non-scientists and non-mathematicians sometimes find equations scary. I just want to say it's only going to be up there for a brief time. If it makes you dizzy, just sort of rest a little bit. But here comes the equation. It's Heisenberg's uncertainty principle. Fuzziness in position times fuzziness in velocity is always greater than 0. Basically, you can't always know exactly where something is and exactly how fast it's going. The product of those uncertainties is always larger than 0. In physics, in language, we write this as delta x, uncertainty where it is, times delta momentum, uncertainty in how fast it's going is always larger than this very small number, Planck's constant. What does that have to do with temperature? Well, suppose we've got a whole bunch of atoms, we put them in a box. And we have lots of atoms in the box, but the box isn't going anywhere. We know that the average momentum of the atoms in the box for every atom that's going this way, later there'll be an atom going that way, because on average the box isn't going anywhere. But if I take the average of the square, if I look, what's the square of that particle's momentum? The square of that particle's momentum, it's not zero, it's a little larger than zero. And that's because we don't know exactly how fast it's going and what direction it's going in any one particle at any given time. So basically, as things get colder and colder, this temperature, which is proportional to the square of that average momentum, as the temperature gets smaller, the average square of the momentum gets smaller, the uncertainty in how fast it's going gets smaller. And therefore, if this number is getting smaller, this number, the uncertainty in where it is got to be getting larger. So basically, it's a natural consequence of quantum mechanics that as you get things colder, they act more and more like a wave, a sort of fuzziness in where they are, and that's called the Broglie wavelength. The Broglie wavelength, then, you can see that this is going to go as well over the square root of the temperature. So here's our explanation of Bose-Einstein condensation. We said that atoms, when you get them cold, they start to act like little waves. This is my attempt to use the PowerPoint program to make a wave. It's supposed to look a little bit like a jellyfish or something like that. You can see that these jellyfish are all quite distinct one from another. It's a bunch of atoms there. If we get them a little colder yet, then the waves get bigger and you start to have the wave of this atom overlap with the wave of that atom. And it's this overlapping wave where one atom overlaps with another atom. That's when you get the Bose-Einstein condensation. What I'm going to do is kind of take a cross-section through there. So you can see, suppose the atoms are all different from one another, and I represent this by making them all different colors. I can draw these as different waves. You can see the waves start to overlap. If the waves were indistinguishable, if the atoms are indistinguishable, if each atom is exactly the same as every other atom, then these waves overlap, and I sort of indicated that by drawing them all the same color. We definitely use all exactly the same atom. If this were a chemistry auditorium, probably on the wall over there, there'd be a periodic table. Our favorite atom is rubidium. So you go over on the left, at the upper left-hand corner, you got hydrogen. Underneath that, you got lithium, sodium, all together now, potassium. I can't hear you. Rubidium, cesium, francium. That's it. Yeah, we use rubidium. It's just, we think of it as like a very heavy hydrogen atom. It's got one extra electron. It's underneath of the hydrogen periodic table, but it's way down. It's very heavy. It's red, which is what rubio means. And it just happens to be a convenient atom for us to push around using lasers. We've got lots and lots of rubidium atoms. Every rubidium atom is exactly the same as every other rubidium atom. They get cold, and the wave of one starts to overlap with the other, and we might as well just draw it as one big line, so we can't tell one atom from the other. And then we do one more trick. We take these atoms, which are so cold, their waves are overlapping, and we draw like a sum of two waves. One is a wave which goes back and forth to the x-axis here, so we're giving you a random part of it. And the other is kind of the offset, a single wave that goes from one side of the sample all the way to the other. And that's the Bose-Einstein condensation. The Bose-Einstein condensation is you have lots and lots of atoms, and they're all doing the same wave. I always think of it as the individual hairs in a giant Reagan-esque pompadour, all sort of piled up like this, all doing exact big same wave. Can't tell them one from apart. That's the Bose-Einstein. You have to get very cold to do that. Okay. We already reviewed quantum mechanics. Now we're going to review statistical mechanics. How many people haven't taken stat mech or thermodynamics yet? Okay, so we're going to review that too. I feel I'm doing a socially useful purpose here. On the other hand, I'm putting a lot of professors out of work because they were hoping to teach you this themselves. But okay. Basically, Bose-Einstein condensation, you have to get cold, and you have to get them close enough together. So this is density